Oh, hello, hello, hello. Welcome back. And when I say welcome back, I really mean welcome back because it is Wednesday, the 28th of January, and I have just done a stream and then my audio kicked out and now I'm coming back on. So hopefully people sort of come back in. And well, the main thing for today is just do the electricity and circuit stuff that I was going to cover. Luckily, heard the oh no through the screen. Yeah, yeah. But in fact, do you know what? I realized exactly what the problem was. Like, I forgot to set the microphone setting, so it was doing the microphone through the webcam, which also means if I watch that old one back, it's going to sound really bad. So hopefully this sounds better properly through the microphone. It's kind of convenient though, because I feel like we just sort of done our little warm up. We'd gone through like the Cambridge offer stuff, done a bit of feedback on that. I got interrupted by a cat, which was very fun. Apologies for not being able to show you. But now I think we can kind of use that as a sort of turning point to then sort of maybe go into the sort of syllabus stuff. But as always, I'm very happy to be distracted by chat. It means I have less work to do. I like that. And for me, tutoring is all about the reaction rather than the teaching. That's why I don't want to be a teacher. So if any guys have any questions, especially now that we're talking about electricity, some people can get kind of stuck up like on that, feel free to pop it down and I'll react to that. But in the meantime, let's get into this electricity stuff. So my main thing here is I got like 40 minutes left before my next session. So what are the main things you got to know if you were taking the exam tomorrow? It's not letting me log into Collude. I don't know what that means. Okay, let me move you guys over here and let's go into the whiteboard. What happens to the potential difference when we have two cells in parallel that had different EMFs? I don't know. I'm bad at that. Okay. I have a feeling that would end up because you're forgetting that there's no such thing as an ideal cell. So the cells also have internal resistance. And so maybe it's set up such that the current goes through them such that the external voltages are the same. That would be my guess. Claude. I don't know Claude. Claude is an AI chat GPT or Gemini thing. Okay. Right, let me get my screen shared and let's start discussing this electricity stuff. Not the entire screen. Chrome tab, my mirror whiteboard. Yes. All right, so we are good to go. All right, so let's go through the essentials again. Not so much like the core edge details, although if you do want those, feel free to drop those in chat. I'm going to mainly cover, you have an exam tomorrow. What is electricity, right? So let's again just sort of go through the basics. So current, let's sort of quickly round out the stuff I think is sort of prerequisites here. So current is the rate of flow of charge, which you know. The potential difference, voltage is work done per unit charge. And then putting these together, you can multiply these together. And we know that power is work done per unit time. But that is work done per unit charge times the charge over time. So it is also VI. Another thing that's a prerequisite here is Ohm's law. All of these, I think, are kind of recap from GCSE, so I'm kind of barreling through them. This should be fine. So Ohm's law, V equals IR. I'm also kind of expecting you guys to have a good grasp on. And by plugging that in, so I is also equal to V over R. And by plugging in this V and this I into this equation for P, you can form the other two forms of this equation, P equals I squared R, and P equals V squared over R. So these are kind of the equations that I would have expected you to come across in GCSE. I will also emphasize while we're here that current is the rate of positive charge. Now, this is one of my favorite stories. Why is it positive charge, you may ask? Why is it not negative charge? It's the flow of electrons. Electrons are negatively charged. And the reason why is because circuits and, well, current was discovered before the electron was discovered. So they knew that charge was flowing and they were like, I don't know what's flowing. And they coin flipped and got it wrong. But by that point, they were decades into using the conventional current as being positive. So by the time they got around to an electron, they were like, God damn it. But they stuck with the convention. Um, okay, so apparently it's impossible for it to have different potential differences. Well, I can tell you, I'll answer that question. Like, I'll kind of come to that when we do the series and parallel circuits. Let me get back to this though. Because I think I have a solution there that you'll quite enjoy. So those are the basics. We know resistance. We know Ohm's law states that the metal conductor, the potential difference is proportional to the current through it if it obeys Ohm's law. Now, because it's directly proportional, it means it should be a straight line through the origin, remembering that that is what directly proportional means. Now, another thing, top thing, resistivity. This is new for the A-level syllabus and is given in your formula book. I actually just went through this with a student today, and it can be tricky where they give you dimensions. So they were given a question where they mirrored a wire, not mirrored, modeled a wire as a cuboid. That is not, I am winning no art prizes for that. Hold on a minute. Oop, close enough. Right. So they modeled a wire as a cuboid of, this was like 0.02 centimeters. This was 0.02 centimeters. And this was 10 centimeters long. And so it's your job to understand that the A in this equation is the cross-sectional area. And you must also know that it's flowing the long way through the wire. So that is the length. And this here is the cross-sectional area it passes through. Now, why does this make sense? Let's rearrange this and say that R is equal to rho L over A. The reason why this makes sense is it makes sense that, because if you imagine from your perspective trying to be an electron moving through this system, if you are facing, the further in you go, the more resistance you're facing. You expect the resistance to go up the more you have to get through. But also, if the current if the cross-sectional area increases, if you think about trying to get water to flow through it, clearly the bigger hose is going to get more water through per second, right? There's less obstruction to water flow. A really small wire really can't let a lot of current through it, physically can't fit it, whereas a thicker wire can fit more current through. So it makes sense that as the current goes up, as the area goes up, the resistance goes down. So that's why this makes a lot of sense. One thing as well they can get you to do, let's talk about this, especially they do this a lot in your AQA, but I know they do it in other boards as well. So talking about a circular wire, in your practicals, the way you do it is you measure the thickness using a screw gauge micrometer, because it's very, very small. So you have to know your instruments and their precisions. So you can use a screw gauge micrometer to measure the diameter. You would measure this in several places and take an average in order to decrease the uncertainty. But you have to remember that the thing that you are measuring is the diameter, and that can often be a trap. They very often give you diameter, and you need to know that the area is pi r squared, which is pi d squared over 4. And a lot of people forget the over 4. So that's a trap. Look out for that. But taking measurements that you're given, you can work out the resistance, or you can work out the resistivity as required. Now, we can also think about how you would do this experiment in practice. How would I find rho? Well, what you can do is to set up an experiment where you measure, so it's like an R versus L graph. So we know that R is equal to rho L over A. So with any experimental physics question, the goal is to get the model in the form of a straight line, which you can then plot. So we know R is equal to rho L over A, which I can rewrite as rho over A times L. In other words, I would expect this to be of the form y equals mx plus c, where c is 0. So I expect it to be directly proportional, straight line through the origin. And I expect the gradient to be equal to rho over A. So in other words, to find rho, you get experimental results for the resistance of a wire of different lengths, plot them, take the gradient, and then rho is equal to the gradient times A, the cross-sectional area. This is how you do it in practice. But then you can think, let's start setting up some circuits to think about experimentally how you would do this. So you would need to have some sort of EMF source, like a simple cell will do. And you could have wires of differing lengths, which you insert in here. So these are sort of a variable lengths resistors. You can swap those out as required. As always, you have an ammeter and a voltmeter. Ammeter in series, voltmeter in parallel. You would measure the voltage and the current for these different resistors of individual lengths. So for a length in meters, you would find the current, which is obviously not A, the current is I. You would find I in amps, you would find V in volts, and from that you would say V equals IR to work out the resistance in ohms. From that, you can plot R against L and then get your resistivity. So this practical is very important to know. I won't go through superconductivity because that's a bit niche. I won't also not go through every single component of circuit diagram. But what I will do is talk about IV characteristics, the 3 classic ones you have to know. So if my exam was tomorrow, I would be holding on to this as a core concept. Nope. Swing and a miss. Right. I should really get the straight lines out, but whatever. So wire, close enough. Let me move this. Is it going to move? Okay. So this is your IV characteristics for a simple wire. A simple wire is ohmic. It obeys Ohm's law. Straight line through the origin. V is directly proportional to I. Now, this is not the same way round that Ohm's law is. Ohm's law would have V on the y-axis and I on the x-axis. So we can rearrange this and say that I is equal to 1 over R times V, which means that the gradient is equal to 1 over R. That's going to become really important for the other two. Well, not the other two, but certainly for the lamp. This is for an ohmic resistor. What we also have is the lamp, where the graph looks more S-shaped. No. I'm gonna get it. I'm gonna get it. All right, so it goes up, and then something like that. So the question then becomes, why does it have that behavior? Often examined syllabus point this. That's not I against R, that's I against V. That's still not it. Okay, so I against V. So remember that the gradient is 1 over R in this case. Well, what's happening here? Well, as current goes up, there are more electrons flowing through the resistor. And what's happening is it's colliding with the atoms in the resistor, or colliding with the metal ions in the wire, and so it's giving them energy. It's heating them up. The temperature goes up as the current goes up. And as the temperature goes up, which you know from solid state physics, thermal physics, that the atoms in a solid are in a regular array and they're vibrating. And as the temperature goes up, they vibrate more. So what's happening is they are getting in the way of the electrons trying to pass through, which means that the resistance goes up. Which means that 1 over R goes down, so the gradient decreases as the current goes up, which is why you get this kind of S shape. Important, this happens in reverse bias as well when you make the current go through in the other direction. And the final IV graph you must know, if you had an exam tomorrow, is the diode, which is forward biased. So the current is 0 up until the point where it really, really isn't, where it goes almost vertical at a set voltage of, it's saying 0.6 volts. So it only lets current through in one direction. I know I said this before, but I should really have labeled this before, that this is for a lamp. Okay, so that's what's going on there. I won't talk about the thermistor too much. Let's talk about, again, if you had an exam tomorrow, what I would be talking about is Kirchhoff's laws, the rules for combining things in series and parallel. So this will be very familiar to the core audience who's staying over from Cambridge applications, but I promise I'm getting to this 2 cells because that's going to be fun. So what happens here is, if we have a junction, current in equals current out. So in this case, if we had I1, I2, and I3, then the current in, which is I1, would equal the sum of the individual currents, I2 and I3. And that's Kirchhoff's first law. If 2 components are in series, they have the same current going through them. So that's not too interesting. Oh, chat is disconnected. Please wait while we reconnect. Successfully connected. Sorry about that. Apologies if you tried to leave a comment in that exact 3 seconds that chat was down. Right. So those are the that's the rule for how current splits up in parallel. Now, voltage rules, we know that if we have resistors in series, and that is R1 and R2 and R3, we know that if these have these different voltages, V1, V2, V3, we know they all have the same current I. And we know that if these are connected up, for instance, to a simple cell of current of potential difference, or EMF V, we know that the voltages add in series. And we know this current is the same throughout. And we also know that the voltage distributes in proportion to the resistance, because in every single case, V is just equal to I times R. Now, a lot of people ask me this because this is something that obviously comes up in GCSE as well. How does it know to hold back any voltage? How do you sort of leave with V? Why does it not drop all of it off at the first resistance it finds? And this is where I kind of use, and this might feel patronizing at face value, but it's genuinely how I think of it for myself as well. But the way I think about it is like a fleet of Amazon delivery trucks model. So the trucks leave the factory, the what's the delivery something warehouse. Let's say warehouse. So there's a kind of warehouse. You've got your like Amazon delivery trucks, non-sponsored, and they have the packages that they have to deliver to the different houses, right? So they all leave with, and they have to drop off all the packages before they come back. That is why this is true. So you pick up the voltage in any closed loop, voltage gained is voltage lost, which is Kirchhoff's second law. So you pick up a certain number of packages, you drop them all off before you come back. So then how does it know? So for instance, we can compare two circuits. So let's consider the circuit where R2 and R3 are not included. So it's just R1. Well, in that case, all of V would be dropped off on R1. But now R2 and R3 are added further down the circuit, and yet this guy knows to take less voltage. Why is that the case? So electrons are sentient. Yes, electrons are sentient. Well, the way I kind of talk about this is, well, let's use again this fleet of Amazon delivery trucks. You're driving on the road. How can you tell that there's more resistance up ahead that you haven't got to yet? Well, the answer is you go slower. You don't need to arrive at the traffic jam to know that there's something that happened in front of you down the road. You go slower because there's more resistance to your forward motion. So by going slower, you're like, oh, there's something up ahead. And the electrons are exactly the same. So they can tell, because of how quickly they're able to flow through everything, whether there's more resistance up ahead. And so they know to only drop off some of the voltage at the first resistance they see, and it kind of works through like that. So I think it's just a really helpful model to get your head around all of that. In parallel, voltage is... What if the electron is drunk? Well, no, you're right. It would be an electron in my model. I was going to say, no, it is. What if the electron is drunk? It shouldn't be driving. It should not be. No, it's January. I was gonna try and do a clever, but no, I'm too tired. Can you just leave in chat the funny response you wish I'd given, and then I'll just pretend I said that? That'd be great. That'd be a-okay, fantastic. I should not do cleverness in January, but it's all right because next week it'll be February and it'll be totally different. So let's consider now things in parallel. We know that if this is a voltage V, let's think about this Amazon delivery trucks model again. We know that it has left with the packages. In this case, the packages are voltage. We know that if once you come here, the trucks can go one of two ways. If you go on this path, the only resistance you see is this. So they must drop off all of the V there and come back to the warehouse empty. Same thing for the trucks, as it were, that go down this path. The only resistance they see on the way is this resistance here. So all of the packages have to be dropped off there. And that is why two branches in parallel must have the same potential difference. Because the electrons here, and here's another top tip. If there is no resistance between a point on the circuit and another point on the circuit, then those 2 points have the same potential. So here, you have all of the V potential left, which means here at this point, you haven't lost anything, so you must have all of your potential V. And you can think about the same thing on the other side. If this is where they come back to the cell, they must have lost all of their potential by the time they come back. This has to be zero potential, which means here also has to be zero potential. So if that has to be V and that has to be zero, then the difference between those 2 points, no matter how you get there, the potential difference must be the same. It must be V. And this is where I think, well, I just need to add one more thing before we get to your idea of cells in parallel. But this is a sort of crucial idea for getting to grips with it. You also know about combining resistors in series and in parallel. Where if we have resistors in parallel, let's take this for instance. If this is R1 and this is R2, I can write this as an equivalent circuit with a single resistance. And what would the equivalent resistance need to be? Simple equation here. 1 over the resistance is 1 over R1 plus 1 over R2. So the reciprocals add. When they were in series, the resistors added normally. Now they are in parallel. It's the reciprocals that add together. All right, so I think there's one more thing I need to talk about before we can start having fun, which is the idea of EMF and internal resistance. So normally, a cell is considered to have an EMF E, but it also has an internal resistance of R, little r, that cannot be separated from the cell. So this entire thing becomes the cell, and we have an external resistor of big R. And what we find, or rather what we know, is again, in any closed loop, voltage gained is voltage lost. Because these are in series, there is the same current moving everywhere, which means that the voltage lost here is I times big R. The voltage lost here is I times little r. This I times little r is what's called the lost volts, for reasons that we're about to see. Because voltage gained is epsilon, that equals the voltage lost, which is IR plus I little r. But this is a voltage that you can measure with a voltmeter in parallel, which leads to the form that I much prefer, V equals epsilon minus IR. Now, again, as I was saying, everything in physics is about forming a straight line equation that you can plot. So in this case, a graph of V against I would look like this. Where the intercept would be the EMF, the true EMF, which you can measure by attaching a voltmeter to the cell without any circuit connected, just sort of in isolation. And the gradient would be minus the internal resistance. So by plotting this graph of V against I, you can work out both the EMF and the internal resistance. Now, let me use this idea to finally answer the question that was posed to me right at the start of this entire thing. This is more of a stretch question, so if you were having an exam tomorrow, I wouldn't stress about this. This is more for the sake of curiosity for the people who are here. The question was asked, what if we have two cells in parallel with different EMFs? So let's say this was a 12-volt battery and a 6-volt battery. My theory is, and you may want to ChatGPT it, so this is maybe more for like Oxbridge interview style. My theory is because these have internal resistance, let's start with what we know. We know that this thing has a fixed potential difference. We know the potential here is 0 in both cases. Oh no, maybe this wouldn't work. No, I think we'd be fine. Maybe. So maybe that's not the 0 point. Maybe we should think of these as a cell, and instead of thinking about what happens inside the cell, let's instead only consider what's happening external to the cell. So that wouldn't become the 0 point. I think that these points are equivalent and must have the same potential difference through them because there just is a current going through this resistor. So there is a fixed potential difference across the resistor, which means there's a fixed potential difference across these points, which will be the same in both branches of the parallel circuit. Which means that my claim to you is that V is the same, even though epsilon is not the same, because V is equal to epsilon minus IR. And I wonder if this is legit. Because I think what that means is they draw different currents such that if this is I2 and this is I3, then my claim is that the lost volts here make up the difference. So in other words, we need to have 6 more volts lost on this internal resistance than are lost here. So I would be saying that I3 times R1 would be equal to I2 R2 plus 6. And then I think it comes right. So that's my claim. Fact check me if you want to in the comments, and I'm very happy to hear otherwise. This is just a comment that was left and me trying to use the problem solving skills that I have from A-level to come up with my best solution. Feel free to drop in the comment chat as well if you sort of have any follow-up questions about that specifically. AI seems to agree. Non-identical cells in parallel fight each other until internal resistance forces a compromise voltage. So this is what I think would happen. They are forced to have the same, which means that the currents go crazy, and then we know that 6 extra volts have to be lost on this first internal resistance to make the external voltages the same. And if there's no internal resistance, it's just the bigger one. But in practice, there's always internal resistance because A-level. You are very welcome. And again, well, actually, do you know what? I might come back to that. I can add that to my list of interview questions to sort of bring on next year. Now, is there anything crazy that I need to go through here? I think potential divider is the only thing I would need to go through. And the idea of a potential divider circuit is like so. So it's really to do with this idea that voltage distributes in proportion to resistance. So let's say we have a cell coming around, and we had a fixed resistor and something like a thermistor. And this, let's say this is V. So they might say, what happens, and let's say we connect our voltmeter up here, and the question might be, what happens to V as the temperature increases? So let's say this is a fixed resistor R, and I'll say this initial resistance is R1. What we know is this initial voltage, it splits in proportion to resistance. So the fraction of the total resistance that R is will be the same as the fraction of the total voltage it receives. So this fraction R over the R total, which is R plus R1, that is the fraction of the total resistance it is. And it will be that same fraction of V. That will be V1. And then what happens is, as temperature increases, well, we know that the resistance of the thermistor will go down. In case you're curious, the reason why, this may be on your syllabus, some syllabuses have the idea of drift velocity, which is proportional to the number density of charge carriers. The idea is that the extra temperature gives electrons energy, which excites them sort of into being conduction electrons. And so you just get more electrons flowing around, so the current goes up, so the resistance goes down. If that's not in your syllabus, all you need to know is that as the temperature goes up, the thermistor's resistance goes down, which means that the thermistor has a smaller proportion of the total resistance. So I'll say that again. Because the thermistor's resistance has gone down, it has a smaller proportion of the total resistance, which means that R is a bigger proportion of the total resistance. Of R total. And so what that means is, so for instance, if it goes to R2, then V2 is R over the new total, R plus R2, times V. But if R2 is less, then this is a greater proportion. So in other words, the voltage goes up. This has a greater proportion, so it gets a greater proportion of the voltage, and the voltage across this cell, the voltage across the fixed resistor goes up. They can ask you to quantify this using your V equals IR and give you a bunch of data. But as in sort of introduction, given that I have a session in 3 minutes, I think these are the most important syllabus points for you to really master if you were to have the exam tomorrow. So I'm going to stop sharing the screen there. I'm going to say, if you have any comments, feel free to drop them. And I'm going to continue. Also, there was, I don't know if, in fact, you might be the one. One of my students showed me the Discord server, and it looked sort of legit. So I think a Discord server could be coming soon, which I would post to it when I'm going live so that you guys get sort of notifications. Because I think even if you're subscribed on YouTube, it can be a bit like as to whether or not you get notified. I know like students of mine that have subscribed don't necessarily get notified that I've gone live. I think this Wednesday at 5:30 slot is certainly stable for now. So it'll be a sort of regular thing for these more sort of seminar style streams where I go through different topics. And I will also continue to do my live solves, sort of peppering them in where I can, demonstrating technique, exam technique and practice, because even if you understand it, it doesn't mean that you're necessarily going to get all the marks. So I'm going to carry on doing what I'm doing. Feel free to keep dropping in. I'm always happy to have suggestions for the different topics that I go through in these weekday evening streams. I know I've had a request for fields, both electric fields and gravitational fields. So I'm planning on, I think, going through this physics syllabus topic by topic and doing this. If the exam were tomorrow, what are the must-know ideas? And ideally, probably having a few more practice questions to demonstrate as well. But yeah, sort of trying new things and seeing what people like. So I'm going to leave it there, and I will see you certainly next week for a live solve and a new evening stream. So with that, work hard, have fun, take care, and I'll see you next time. All right. See you guys. Bye-bye.